Welcome to section 4.2, where we will be learning about compound inequalities. We will be graphing a compound inequality on a number line, as well as solving a compound inequality. Let's get started. A compound inequality is two or more inequalities that are connected by the words and or. And the and cases, we can actually write it together, and we'll see that in a little bit. The first type of compound inequality that we're going to talk about is the intersection, which is the and. So for example, if x is greater than -1 and x is less than or equal to 3, where is it true for both? So we need to find the solution set where x is greater than -1. So I'm going to go from -1 to 3 here. So I'm going to make that be my number line. And if x is greater than -1, that doesn't include it because it's not or equal to. And it's greater than -1, so it's going to be everything to the right. So I just put an arrow to the right with shaded to the right with an arrow, because in the end, we're going to really highlight what the final solution set is. All right, we also need to graph x is less than or equal to 3. So that is a closed circle on 3, and we need to shade all the solutions that are less than 3. So technically, all the solutions greater than -1 would look like that. All the solutions less than or equal to 3 would look like that. Well, the solution of both, the intersection, is not the entire number line, it's just where they're crossing, and that is from here to here. So my final answer is here on the bottom, and that's showing all the solutions from -1 to 3. We did this with domain and range and 1.1. We've seen this notation before, and we know that the lower number goes here, the higher number goes here, and we're saying all the values in between those. And this is an open circle because it's not including -1, and that is a closed circle because it is including 3. Our next compound inequality has to be separated with an or, and we'll show why here in a moment. It's also called the union of the two compound inequalities. So we're going to have -2 and 1. So let's make our number line. I'll graph a couple of those here. All right. So all the values of x that are less than -2. So I need to shade everything less than -2. So an open circle on -2, I'm going to shade everything to the left. Now, for x being greater than or equal to 1, we need to shade everything that is equal to 1. So I'm going to do a closed circle, and all the values that are greater than, that's to the right here. So as you can see, they're not overlapping at all. So if we were looking for the intersection, the and, it would be no solution because they're not crossing anywhere for both. But if I have an or, where is it true for this one or this one? It's everything that's shaded there. So all of these in between are false. -2 would be false, and all of those would satisfy at least one of the inequalities. So the or means your solution set is satisfying at least one or the other, not just both. And very, very, very importantly, we cannot write unions or the ors as one compound inequality statement. You have to have an or for the ors. This is saying in between 1 and -2, and that just doesn't make sense because that's not the lower number and that's not the higher number. So we just cannot write it that way. If I see notation like this, I'm assuming it's an and where they're intersecting each other. I just realized that I copied the same examples for the next two. I apologize for that. So -1, 0, 1, 2, 3. If you really want it, it's an open circle on -1, closed circle on 3, and we're saying all the values in between those because this means -1 less than x and x is less than or equal to 3 when it's written in that notation. All right, for this one, same thing. I apologize that it's a repeat. All the values are less than -2 or greater than or equal to 1. I'm not looking for the intersection because of the or. I'm just wanting to know where it's shaded for either of those two inequalities. This next one has an and. So if x is greater than -1, going that way, and 0, 1, 2, 3, if it's less than or equal to 3, it's going that way. So technically, kind of the whole number line is shaded right now, but we just want the intersection of the two. So open circle to closed circle, it is indeed the same example that I had earlier. Please hit pause and decide which inequality is represented by the graph. Now that you've done that, let's take a look. Looks like -4 is part of that number line. 3 is part of that number line. -4 is definitely an or equal to case, and 3 is not. But the question is, which way do the symbols go? So I'm saying all the values that are bigger than or equal to -4 and all the values that are less than 3. And how would we write that? Well, from -4 to 3, it looks like they're all like that, except for D. D's got -3. We can throw that one away. I see closed circles on some of them, but not both of them. So I could throw letter A away because of the or equal to cases. And -4 is the solution of this graph. So that has to have the or equal to, where B does not have that. So letter C is correct. Now, as you notice, we've got two inequalities separated with an and. That means this is a compound inequality. So we are going to solve each of these separately. So please hit pause and try that because that's what we did in section 4.1. When you're ready, go ahead and hit play. All right, we treat this inequality unless if we as an equal sign, unless if we multiply or divide by a negative, then we need to flip it. Besides that, we're good to go. So to isolate x here, we need to undo the 2 and the 1. So we're going to undo addition with subtraction first. And then we're going to undo multiplication with division. So we know that we need to shade everything that is greater than or equal to 1. Well, 1's right here. I need a closed circle, and I'm going to shade to the right, because that is greater than or equal to. All right, now solving the second one. Solving for x, I need to undo multiplying by 3 and subtracting 4. So I'm going to undo subtracting with addition. And undo multiplication with division. So I also need all the values that are less than or equal to 7. Well, there's my 7, closed circle. I need all the values that are smaller than 7 because that would make it true. Now, the most important part of this right now is that these are two inequalities not separated with an and or an or. Our final answer has to have an and if we started with an and or an or. And as you can see, they're running into each other. So my final solution set is everything from 1 to 7 inclusive, because we're including those endpoints on both ends. And I can write the ands as this kind of compound inequality without the and because it's already assumed. Here we're saying x is greater than or equal to 1 and less than or equal to 7. It's assumed in it as we read it. Here we have to solve and graph again, so please hit pause and try to do so. We have two inequalities separated with an or. That makes this a compound inequalities. I want to know where it's true for this inequality or where it's true for this inequality. All right, so let's subtract 1, divide by 5. So x is greater than 4. And for this one, we're going to subtract 2 and divide by 3. That's just a less than, that's not or equal to. All right, now our final answer has to have the or in it. It's what we started with, we need to end with it. So I need to find all the solutions that satisfy x is greater than 4. So open circle, because 4 is not equal to, or I'm sorry, 4 is equal to 4, not just greater than, so we have to leave it open. And all the values of x that are less than -1. So open circle on -1 and all the values less than that. And because it's an OR, I'm not looking for the intersection where they're both crossing. I just want one to be true or the other to be true, and that will satisfy the compound inequality. So everything here makes both equations false. That's why nothing shaded. Everything here makes this inequality true, and everything here makes this inequality true. So it's true for this one, or it's true for this one. That's what we graphed. The last example is also compound inequality. We saw that earlier, but this time x is not in between. So something subtract 4 is greater than -3, and it's less than or equal to 2. So we can separate those. -3 is less than x subtract 4, and it's the expression x minus 4 is less than or equal to 2. I strongly suggest a lot of you doing that because you can isolate this x by treating it like two equal signs. So to get x by itself, we have to undo that -4. We're going to do that by adding 4. But however we do to one inequality, we have to do the other side. Well, that is also true for the right side. So we have to add 4 not only to the -3, but also to the 2. All right, so that -3 plus 4 is 1. We're left with x, so we isolated our variable, and 2 plus 4 is 6. So this is saying all the values that are greater, read it from the letter, all the values that are greater than 1 and less than or equal to 6. So 1 is here, and we want all the values that are greater than 1, not less than 1. And then we also need everything less than or equal to 6. And I'm not looking for either of them. I don't want it where it's true for this or this one. I want to know where it's true for both, for this one and this one. So here, just shade our final answer in between 1 and 6, but does not include anything left to the 1 or right of the 6, and also not including 1. I hope you understand a lot more about compound inequalities and that you can do your assignment. Please ask questions, come in after school. We've got math lab every day except Wednesdays. There's always a math teacher here to help. So take advantage of it. Fill in those gaps and move on and be a stronger mathematician. Have a lovely day, everybody. Take care.